Welcome back, everyone, and we're back for another video, and we're continuing with ray intersections. The next object we're going to deal with is capsules. Now, capsules is a more complex object because it's actually at least two objects, or you can say three. It's two spheres and a cylinder. That's what makes up a capsule. Capsules are very useful and used a lot in collision detection. Sometimes you encompass the player character inside a capsule boundary type of thing to detect collision between the objects in the world and the terrain and everything else. One problem is you don't actually find a lot of information with ray intersecting capsules. So even though there's a lot of good images, all of these are related to collisions, and the NVIDIA one image is really just showing their psi X library. So they do have a ray intersection, but no code of how it's done. It's just a library to use. So we're going to explore capsules intersection. So it's really two intersections you need to test for. It's the cylinder, and you need to test for spheres. All right, so I want to say that I managed to find a good algorithm from Stack Overflow. We're going to be using this chunk of code this person provided in their question. Bill Cotes, I'm sorry, I can't say your name, but this Stack Overflow equation was the one best algorithm I was able to find that's useful. Apparently, when it comes to cylinders, the algorithm that most people are using or really just talk about, like if you're searching for it, is that they try to keep cylinder into local space, and then you have to bring the ray that you create into local space, or sometimes they call it object space. And to me, I find that a little weird to actually have to move the ray and the cylinder into a new type of space just to do a hit detection. This algorithm does not require all that movement. It actually can do cylinder detection, and it can do it in world space at any rotation and at any scale or translation. So I'm using this one. This is the only one I found, and I can't really find any information about this specific algorithm. So I have a hard time really going to explain or visualize how this bit of math works. So, but it is the only one I can find that works in world space. Like a lot of things you find online, everything has to be pushed into what they call object space, and you have to do all the testing there. I don't want to deal with that. I really just want to keep everything in world space, just like every other ray intersections we've been doing. Everything's in world space. We don't move anything around into these weird dimensions. So there's going to be a little black hole when I try to explain this part, because I can't understand most of the math. I know what certain things are doing, but I don't understand why. I don't know if there's like a certain triangle that we're looking for, or things like that. This might be something called like quadratic equation type of stuff, and I don't know quadratics at all. So this part, we just have to take the word for it that this works really well, and it does. It's the only one I found online. I just couldn't find any more information related or what this algorithm is called. So if you guys know the name of this algorithm, please by all means tell me if anyone knows this one, and I'll probably make a supplement video about this and maybe go into more detail of how it really works. Like what are, if there's triangles or there's anything funky that I can visualize to make it a lot easier to understand what's going on. So yeah, we're going to do capsules. We're going to use this equation. We're not going to use all these if statements. He's trying to optimize detection. But for me, I'm just going to use bounding boxes. So I'm going to, I'll detect the bounding box first, and if it's within there, then I will do cylinder detection. So I'll just save myself time just by doing AABB first. And normally that's really how it's done anyway. In a lot of game engines, you always test A/B bounding boxes first, axis aligned bounding boxes first, and then you go into the more complex intersection testing. And one thing I should note is that this is an infinite cylinder detection. This thing only can detect a cylinder that's infinite. All right, so let's start looking at some code. So we have our bounding capsule. So it's a new file inside entities, and you can define a capsule, or actually say a capsule. You can define a cylinder in several different ways. One way to define a cylinder is a point, a direction, and a radius. Another one is 2 points and a radius. And the third option I find the most complicated, which I don't even know why would you go through that, would be a center point, a length, and a direction, and a radius. I decided that what makes the most sense for me to define a cylinder is that I want a radius, a start, and an end position. I can determine a direction by just subtracting these two, which I probably should. So this way you don't have to do it in the ray intercept function. But again, like I said, all this stuff is just prototype and just to really get to see what the algorithm is all about and what it's for. And then in the next video, I'm gonna do terrains, and that one I'm actually rewriting everything in the proper way. So this way, everything, you'll have a ray object that has all the information that we need for it, and things like that. So this way, and the visualization and the data is going to be separate. Like right here, the bounding data and the visualization is together. Where next video, I'm going to start breaking that apart. So you can start using it in real world applications. But like I said, this is all for prototype, and this is all for kind of learning. So that's the definition we're using. We're using radius, start, and end position. And this image kind of always shows you, like, that's the main definition really of a cylinder. It's just the point A to B, and then you have your radius. It goes around a circle, and the radius that you go around in a circle is the same radius of a sphere, so everything kind of just fits together. The generation of our capsule is similar to the circle one from the previous lesson, except during the halfway point, I stretch out and duplicate the vertice, and then can kind of continue. And it follows the same idea of a line strip. So even though it's a 3D mesh, it's one continuous line that generates the shape. Like I said, it's so yeah, it's probably, I'm doing it slightly differently, but it's the same idea from the previous lesson, which we did with spheres. So you can get all this stuff at GitHub if you don't want to type it all out. There's tons and tons of comments to kind of explain everything. I'm very, I always like to explain what variables are. Since I don't use big long names for variables, it always makes good idea to comment these small names, so anyone who comes in can understand what's going on. And if I come back here a year from now, I'm like, what the hell does v half means? Like, oh, it's the halfway point to extend the sphere to make a capsule. Okay, so I try to do this for myself and for everyone else to understand my variable names. So now we're going to start doing some good stuff. Everything is the same for the most part. We're going to bring in our bounding. We're still using our same shader. Just calling it cap. And then, we just put it on the scene. We got some positions and rotations to really mess around with. We're going to use in-cylinder test to start with. And, we got our regular stuff. We got our points. We're visualizing our line, our ray line. And we're passing our right. So, in a lot of previous lessons, videos, I always try to remind you that everything kind of needs to be in world space. And a lot of times we don't deal with rotations. The only time we dealt with rotations was when we did oriented bounding box. In this lesson, because I really wanted to make sure that that algorithm that tests cylinders actually works in I guess axis or object aligned. I start adding some rotation. So the first thing is the first thing we got to do is bring our cylinder into world space. So we already know what its rotation is and we know what its position is. So we need to bring it in. And like I said, since a cylinder, the cylinder that I defined is 2 points, it makes it easier just to rotate 2 points. That's why I didn't bother making a point in a direction. It's because I would have to rotate the direction, and I just don't want to. It's just easier to take 2 points and rotate it 2 points and call it a day, because then I have to calculate everything else. So that's what we're doing here. We're making copies of our A and B point for our cylinder. We're going to apply rotation, and we're going to apply our translations. The only thing that's missing is scaling. You do the exact same thing. You just add scale, and I think the order is you rotate, you scale, then I think you do translation. Or you can do scale first, rotate, then translate. You should always do translations last. It depends on what you're doing, but in this case, you should really do translations last. If you're doing like an orbit thing, you do translations first, then you rotate. But that's if you're doing an orbit type of thing. But we're not doing orbit. We're not orbiting, so translations last. So I didn't want to do scale because I'm not dealing with scale, but scale is the same thing. You just scale it. You just apply a scale. It's just the multiplication on all 3 axes. So once we have that, we're going to visualize our line that defines our cylinder that's inside our capsule. So we go over here, refresh. Here's our fancy new cylinder. We're going to shoot a ray out, doesn't matter where, and there it is. This is the line, and this is the other 2 lines to help define the border of our cylinder. Everything above is a sphere. The other bottom half is another sphere or half a sphere. And like I said, when I was building creating the actual rendering of it, it's really, like I said, just a sphere, and that one point is stretched out, and there's your capsule. So we're going to visualize. So this is the point. Now the algorithm is an infinite cylinder thing, so I can shoot an array anywhere, and I should be able to get a cylinder that's infinitely in this direction from pole to pole. So it should be infinitely going up in the y-axis or down. So that's the first thing we could do. Now this is the part I really can't explain too much. This is the algorithm ported over into JavaScript. You just get the length of the capsule. I think you also have to get the direction. Like the length start. Well, this is the between the ray and the starting point of our capsule. Like I really did try to take this apart and understand it. Like I said, I really can't really visualize or show you how all of this stuff really works. So I can just quickly kind of just click, and like I have everything kind of just out there. Here's the distance. I think this is AB or AO, whatever it's called. Yeah, AO, A to origin. And we got some cross applies. And so somehow these 3 things allow us to figure out an infinite cylinder. And the thing is, it's unlike a sphere of intersection where you can use triangles. This one's a slightly different because if I were going to guess how this works, especially since how certain things look like, you might be defining a plane. I might be wrong. and then doing some type of circle that's kind of rotated. So when I see a lot of cross applies, it usually kind of makes me think that there's direction being determined. So you can kind of handle it. But like I said, unlike a sphere, when you shoot a ray, it can be very tricky how to determine it, because let me see if I can shoot a better ray right through there. No, like this, from point to point. So you're going right through the cylinder. So it's like these weird 2 points. So it's not like a perfect circle. You can find the 2 hits. And in this equation, it does not find the 2 points of intersection. This only finds the single point of intersection. So sorry about this part. I really can't explain too much of it because I don't understand how it works. Now the rest I can, because I did write the rest myself. All right. So the next point is that now we have all this math kind of figured out for us. Like I said, since all the variables don't have explanations, I can't really tell you what's going on. But by process of testing and playing around with it, I'm assuming D has something related to distance. Because if D is less than 0, then the ray, let's say if this is our cylinder, the ray is outside the radius. So somehow, if it's less than 0, it's outside the radius. That's, like I said, when we're dealing with spheres, we were able to just test by radius. But like I said, since I don't understand how this equation works, I can't tell you why it works. But if D is less than 0, we miss. If D is greater than 0, then it's within the cylinder. Like it kind of goes through the cylinder. But it goes through the cylinder that is not through the poles and not parallel to the center line. Well, it does count. It does pass. So as long as it goes through the cylinder in some fashion, a D, if it's greater than 0, it does count. So yeah, if it's less than 0, we return. We're done. It's no collision at all. There's absolutely no collision whatsoever. Now this part does a test on T. And in a way, it does test for parallel. I was getting T and D confused. This T tests for parallel. So if T is less than 0, then the ray is going through the poles. So if we see this black line, if it goes around in a circle to create like a flat top, if it goes through those 2 circles, or if it goes, let's say in the capsule, if it goes through the 2 spheres instead of the cylinder itself, like through the cylinder across, T will be less than 0. Now at that point, there is no intersection point. There's no intersection of the cylinder because the algorithm is an infinite cylinder. So it only does intersections going around, kind of like a spiral. That's an infinite spiral, I guess, in a way. So at this point, if it's going through, it is it's going through the cylinder in some fashion, but it's going through the poles. It's going through the caps. At this point, I decided, normally a lot of algorithms I've seen, they test the 2 poles and see which one you're closer to. But if I'm going through the poles, right? So if I'm going through the poles, why should I test the 2 cylinders or the 2 spheres to see if there's intersection? There's no reason for it. If I'm going right through, I can easily test the length of the origin of the cylinder, or point A, and the origin of the ray. If A is the closest one, has the smallest length to ray origin, then just test this cylinder. If it's this point, the bottom half is the one closest to it. If I shot the ray the other direction, if that point is closest, I test the bottom cylinder. So instead of doing 2 cylinder intersections, just by testing length, we can just say, well, we're testing the top or we're testing the bottom. We save ourselves 1 intersection. So this little, like I said, this little part I kind of came up myself, and it works fairly well. So that's what we're doing here. We're using the square magnitude And so we're going to take A minus this square magnitude. That's position A and position B. And if A length squared is less than A length 2, then we're doing the top cap. Else we're doing the bottom cap, and we return. So at this point, we're done dealing with cylinders, and now we have to test one of the caps of the cylinder. And it could be the sphere, or it can be a circle. Because remember, if you want to do just cylinders themselves, you can kind of replace the that's why I'm not doing it here yet, but I guess I'll get to it later. So now like I said, we're done testing from pole to pole. If the ray does not go through the pole, is not parallel to the line that defines the cylinder, that means we're actually in the cylinder. So now we're just going to test for the lines of a cylinder. And a lot of it is the same as in the previous lessons. We get our since we have our t value, we can just use that t value to create a projection. Is it? So yeah, we got the intersection point. So yeah, that's our intersection point. I'm doing extra things here though. So since we have t and it's greater than 0, that means it is not parallel. It kind of intersects the actual cylinder part of the cylinder. So at this point, we're done. We have the point, but there's an issue. It's an infinite cylinder. So let me just quickly illustrate. If I shoot the ray up here, it finds the point intersection, and it's within the bounds of the cylinder. Like I said, we can't really tell, but if we go up to the bottom, we kind of tell that it is part of the cylinder. So I can shoot it anywhere, and it stays in the cylinder. So like I said, I'm not testing the bounds of the circle or the bounds of the sphere. So it's still part of that cylinder. It's infinite. Now, that's the red dot is the point of intersection. Now you might be like, what's the blue dot? The blue dot is illustrating where on this line the line of intersection projects. So the idea is that I'm taking the length of this and projecting it onto this. Or actually, no, that's not what I'm doing. Let me look at what I did before. So I am taking I'm creating the length. Oh, I guess I am doing that. I am doing projection. Okay. I wrote this and I forgot. So I'm doing the vector. That's why I said it's very important to write comments, because then you forget what you're doing. So I'm doing the vector length between the intersection and the cap line start. Okay, so I should have visualized it. So what I'm actually doing, that's the problem. I didn't visualize it. I'm making a line between here and here. So that's what I'm doing. I'm making a line between here and here. And we have a line that makes the center line. So I am going, so what I want to do is I want to project this invisible line that I don't have yet. Maybe I should just write that code. Can I write that code really quick? I probably can. Why not? Let's do it. Let's because this drives me nuts. And that's the wrong line. Let's find some. Here we go. Let's do that. Let's put that right here. I gotta remember to update the GitHub. All right. So I want to visualize from point A, and I want to visualize to I position. And let's make it a red line. So in the array, color array, red is 0. So if I refresh, I shoot a line. Did I break something? Oh, there we go. There we go. Beautiful. All right. So like I said, we're creating this line. So now I'm visualizing so we can see it. So you can stop pretending to see a line. So I'm going to project this line onto the central line. And that's what the blue is. Now, why am I doing this? Well, because like I said, the problem with the algorithm, it's an infinite cylinder. And the cylinder stops here. And the cylinder stops there. So I need to know if it's still within this. Like, I know it intersects it. Like, I know it's within the bounds of the sphere or the cylinder, but I need to know where on the bottom cap it connects to. So if I shoot through here, it finds the right intersection point. So no matter which part, like as long as I'm shooting through the cylinder, like through that boundary spot, I find that point of intersection. But once I'm here on the lower halves, I'm missing the spot a little bit because I'm testing. Probably easier if I shoot it through the bottom like that. See, it's the wrong spot because I need to test for the sphere and not for the cylinder. So, like I said, by projecting the length of this distance onto this line, I can determine if this is past this border. So I end up by making that projection, I create a value between 0 and 1, and if that t projection value is over the value of 1, that means I'm past that boundary. So that's what I'm calling t limit. So that's what that blue dot is the position of t limit based on this line direction. So if the limit is between 0 and 1, we're hitting the cylinder. We're shooting it right between these two lines. It's perfect. If the limit is less than 0, we're testing the top cap. So like I said, since I'm testing, since the start is A and the end is B, so that's 0 and that's 1. If it's less than 0, I'm above. I'm above this line. And if I'm greater than 1, I'm below this line. So by knowing that, I can determine which cap I'm testing. So if I'm less than 0, I'm testing the top cap. And if I'm greater than 1, I'm testing the bottom cap. The end. And that is this infinite cylinder, right? And then capping it based on this length. And that's the gist of this. And that's really just the algorithm for like I said, an infinite cylinder. Then at the end, we do a little bit of extra testing to make sure that we're within the bounds of our cylinder. And like I said, the only reason why we're testing for the bounds is because we need to start testing for the caps. All right. So with that all out of the way, we can say goodbye to in cylinder, and we can now start looking at in capsule. Like I said in the previous videos, I've been trying to show you the test function, which has all our garbage, and then bring everything down to a more streamlined function. So here's everything from the previous function. It's just everything has been streamlined and taken out. I keep a lot of the comments in there because it's important. And I do make a note that we should include scale. And as you can see, I did this in a chaining reaction way, where before I did them separately. Another option that you can do is that if you have a transformation matrix already, you can just multiply the transformation matrix onto A and B. That's another option you can do. But like I said, I'm only testing for rotation and translation, so that's why I'm doing it. But like I said, if you want to deal with scale, you can add scale manually as well. Or if you have a translation, like a transformation matrix, like the world matrix already set up in your environment, then you can do that. But like I said, I want this function built in a way that you guys can reuse it in any library, so you're not stuck dealing with fungi. So that's why I'm illustrating here. Just rotate this, and then you add translation, add scale. But again, if you have the world matrix already in your environment or using fungi, then maybe just do the matrix transformation on each point. So this way you get everything done in one go. So you got that. Here's our funky algorithm that does infinite cylinders. We have our tests. We test to see if it's within kind of like the radius of the cylinder. We have our test to see if it's parallel. It goes through the caps. And I streamed it down. So I have a function called inSphereCap. And I just pass in which point I'm testing on, A or B, based on the length. So like I said, when you make optimized functions, they're less readable. That's why I kind of have this test functions, because everything's kind of broken out to make it easier to read. But like I said, so yeah. So at this point, we're testing our caps and return our test caps. And like I said, I rebuilt the sphere function from the previous lesson to make it more useful this way, so I can pass in the information easier. So if it's not parallel, then we're going to do the boundary test, and like I said, if it's within the boundary, we're going to pass in our IPOs. That's our intersection point. If not, then we're going to be selective of which sphere to test. So we're not testing both end caps. We're only going to test one end cap. But since we have the information there that tells us where we are, or we can find information that which one is closer, better off that way. And here is the inSphereCap. It's the same thing from our previous video. I just probably changed it a little bit to pass in certain bits of information, so we don't have to calculate it. And if you guys really want to do like actual cylinder detection and not actual instead of capsules, I included the InCircle, I guess the dirty version of it, from like a couple of videos ago. So this is a array to circle intersection algorithm. So if you want to test for a cylinder, instead of using inSphereCap, turn this into inCircleCap, and just fix it up as a challenge if you like, if you want to do cylinders. But if you want to deal with capsules, you got the SphereCap function all built and ready for you to use. So if I click save, click refresh, and I'm able to shoot array, and it finds the point of intersection exactly where it needs to be. It goes, it's right there, it's right there, right there. And remember, when you're testing before, like low below, it would be in the infinite cylinder spot. Now it's actually where the sphere is, because now we're testing the caps. If I shoot it here, no intersection. If I shoot it there, no intersection. Do it there, no intersection. And for final tests, to make sure everything is beautifully working, we have to bring everything into world space, or custom, because right, everything now we're doing is local space, because I'm not moving it from any direction. Now I'm moving it. Now if I refresh, now it's in a different spot. So if I shoot it right there, it finds the intersection point. Now if I do the test right from pole to pole testing, it knows that's the spot, and there you go. There you go. Finds the spot of intersection of a capsule. Very easy. So if you want to shoot a gun at like a humanoid character that's running around your world, now you can. You can just boom, found the spot of intersection. The end. And like I said in the very beginning, you want to do a boundary box testing first, because bounding boxes, axis-aligned bounding boxes, are the quickest, easiest intersection you can do other than the cylinder. So you want to do that first before you deal with this, because there's more math and you have to do testing on the caps for your thing. So that's the only thing you probably have to do, is just add the AABB testing first. If that's successful, then you test your capsule. So yeah, and there you go. In the future, we're probably going to use this capsule thing for collision detection. But for right now, we're just dealing with ray intersections because we're dealing with a lot of ray intersections now. And once we get into physics things, then we might start dealing with collision detection, which is just object to object intersections. Basically, instead of intersecting a line, you're doing object to object, and collisions are, I guess, a complicated thing because it's object to object. You have to make every combination. Circle with every other object, cylinder with every other object, cube with every other. Cube versus cylinder, cube versus circle, cube versus a collision is a lot more complicated because you have to variation, and I think there's like lots of libraries online, so we can probably find like a quick library and that explains the math a bit. So I don't know what to do when we'll get to that point. I'll figure out what to do, but right now we're almost done with ray intersections. So we got one more video to go, and I still need to finish writing the code, which is terrains. I found a good video by Thin Matrix that writes a really good concept of how to find intersection on a terrain, because very little information about it. He's probably like the only one that really talks about it, that teaches it. Like there's no Word document or video other than I think the Thin Matrix that does terrains. So and it's kind of like it's a ray marching thing. So it's kind of like you're testing. But yeah, I'm doing some creative things with what he did too. So like I'm taking his idea and I'm taking it like a step further. And again, I'm using A/B. Yeah, so I don't want to waste too much videos talking about the next video. So yeah, that's our cylinder. Or not, well, that's our cylinder and our capsule detection. So you got both in one go. Sorry I couldn't explain the math part too much, but at least you got the visualization, you got code. You, as a challenge, try the circle caps instead of whatchamacallit, the sphere caps. And don't forget, like and subscribe. Got questions, ask away, and see you guys at the next video.